Chapter 4, Section 4, Factoring Polynomials. We've been adding, subtracting, multiplying, dividing them. Now we're going to factor them apart. This is just like what we were doing with quadratics. Quadratic is a polynomial. These are just bigger, okay? So we need to try to factor them and factor them completely with integer coefficients so that it's no longer factorable. Okay, so the first thing we're going to look for, always, every time, all of the time, is the GCF, greatest common factor. This is important. Look for this first every time. Then, if you can, keep going. So let's look at A. X to the third minus 4x squared minus 5x. 1 and 4 and 5 don't have anything, but x to the third, x squared, and x do. They all have an x. That leaves me with x squared minus 4x minus 5. And now I have a quadratic, and I can factor that. X, factors of 5 that subtract to 4. That would be a 5 and a 1, and I need to be negative, so it's going to be 1 minus 5. So negative 5, positive 1. And now everybody's factored as far as possible. Okay. Now let's look at the next. 3y to the fifth minus 48y to the third. Well, 3 goes into 3, 3 goes into 48, so I'm going to pull a 3 out of there. And y goes into both of them. One of them has 5 y's, the other one has 3 y's. So I'm going to do at least 3 y's. That leaves me with y squared minus, and then we've got all the y's are gone, but 48 and 3, if you don't know, let's see, let's try it. We can pull up the Desmos, but just 48. 3 goes once, 18, 16 times. 16 times is good because that's factorable, and that's one of those special cases. That is a difference of squares. I could treat 16 as 4 squared. So that's 3y to the third. And then in each parenthesis, one gets a y. Each one gets a 4. One's plus, one's minus. That's the difference of squares. Now this last one, 5, 30, and 45. 5 goes into all of them. Z to the fourth, z to the third, z squared. They all have at least z squared in them. That leaves me with z squared plus 6z plus, what do we got here, 9. I can factor that one. 5z squared. Each one gets a z. Factors of 9, 3 and 3 that add to 6, and they need to be positive, just like that. All right, here's a few. You give them a try. Give it a pause. Try them out. Come back. See how it goes. Okay, here we go. This first one. I can pull out an x. Leave me x squared minus 7x plus 10. And then I just want factors of 10 that add to 7. 2 and 5 work. 2 and 5, and then they both need to be negative, so I get to negative 7. And there's my answer. 3 into the 7th minus 75 into the 5th. So I'm going to pull out 3 into the 5th. Leaves me with n squared minus 3 goes into 75 25 times. That's the difference of squares. I could do it as 5 squared. So 3 into the 5th. N, 5, 5. One's plus, one's minus. That's the pattern with difference of squares. If you needed to, 3 into the 5th, n squared plus 0n minus 25. And you go factors of 25 that subtract to 0. Well, 3 into the 5th. 5 minus 5 gets you 0 if you need to do it in that manner. But learn the pattern. It's faster. 8m to the 5th minus 16m to the 4th plus 8. Oh, 8 goes into all of them. M to the 3rd's in all of them. That leaves me m squared minus 2m plus 1. So that's 8m to the 3rd. And we've got m in each. We got 1 in each, and they need to be negative ones so that they work. That's also a style. That's a perfect square trinomial. Okay, so there's our answer there. I guess I should have circled my answer here as well. Okay. Now, in part B of example 1, so if we go back and look at example 1, part B, there we go, there it is. The special factoring pattern for the difference of two squares was used to factor completely. There are also factoring patterns that you can use to factor the sum of the difference of two cubes. Now, this one actually is a pattern you have to memorize, because it's really difficult to try to break these apart in a way. You can treat the difference of squares as a regular factor because you just put a plus 0 whatever variable in the middle of it and just say these must subtract to be 0. But with these cubed patterns, they don't work that well. Difference of squares only works if it's a difference, but cubes works as a sum or a difference. So here are the two different patterns. You got a to the third plus b to the third and a to the third minus b to the third. And there's a pattern to them. Okay. Here's the way that I memorize the pattern. It's all about the a and b-ness of it, the cube root. So you have to know the cube root of the thing, each piece. Okay. And you're going to have, in both of these, they both have a beginning singular to the first degree pattern in front that matches what they are. The signs after that are the opposite. So I'll do those in orange. You notice that they're opposite of whatever the first thing was. And then you're back to, and actually I'll do it in a different color, the back one is always plus. Okay, so these match. These are opposite of this. And then this is always plus. That way it looks like always is always plus. Okay. And the way that it works is it's a quad here. It's a perfect square. So you got a squared thing, you got them times each other, you got a squared thing. It's all, it's almost a perfect square trinomial. It's not 2 times AB in the middle, but it's almost there. So a cube root plus the cube root in one parenthesis, then the first cube root squared minus them times each other plus the second cube root squared in the back. So here's an example, 64x to the third plus 1. Yes, it even applies to the coefficient in front of the variable to the third. But we've got an x to the third, we got a 64 to a third. 64 to the third is actually like 4 to the third, which we can group into one parenthesis. That's there. So we've got 4x to the third plus 1 to the third, because 1 can always be considered a cube or a cube root. And so the first parenthesis, it gets a 4x and a 1 as a plus to match up. And then our next parenthesis is going to be opposite, or our next sign is going to be opposite. 4 squared is 16, and then x squared is x squared. 4 times 1, or 4x times 1 is 4x. And then our last one is 1 squared, which is a 1. So we need to be able to recognize that we have a cube thing plus a cube thing, or a cube thing minus a cube thing, and follow the pattern. Reference back to this screen or reference back to this page in the book to be able to use the pattern until you get used to it. So here we go. And I've got the patterns up here in the right-hand corner. So let's look at A. We got x to the third minus 125. Okay. And if you're not sure, grab your calculator. Okay. The root button, that one is just the square root. So we don't want that one. You have to go to the functions. If you go to the miscellaneous, there's an n root button here in the middle. And now I can do the third root of 125, which is 5. So this is basically 5 cubed. So I have my pattern, right? And I'm going to do a match. It's going to be opposite, and then it's always plus at the back. And I'm going to do an x and a 5, and this is an x squared. That's going to be a 5x, and that's going to be 25, because that's what 5 squared is. And it's just that pattern over and over and over again. Let's look at B. 16s to the 5th plus 54s squared. Okay, that's kind of a weird deal. We've got a squared thing in here. We're supposed to be looking for cubes, so we need to get that out of there. Plus, 16's not a cube, and 54, that I'm aware of, is not a cube. So what we do is get something out of there that goes into both of them. We know the s squared goes into both of them, so we can get that out of there. What goes into 16 going to 54? Let's see. What's 54 divided by 16? Nope, it's not that one. How about 8? Nope. How about 4? Nope. How about 2? Okay, goes 27 times. So we could pull out a 2 because they're both even. We get 8s cubed plus 27. This is good. If you're not sure about cubes, get out your cubed list that we started at the very beginning of the year. We've got a whole list of cubes all the way down through the 20s. But 8 is 2 cubed, and 27 is 3 cubed. So this one's going to be a 2 and an s. So we've got the 2s squared we pulled out already, greatest common factor, right? And now we've got that middle one and the open. This one's going to match as a plus, so that one's going to be minus. This one's going to be plus, and I've got all my zones. I'm going to put a 2s in the front, and I'm going to put a 3 back here. 2s squared would be 2 times 2 is 4s squared. 2s times 3 would be 6s. And 3 times 3 would be 9. So this was 3 squared. This is 2s times 3. This was 2s squared. And those were just by themselves. That would be my answer. Okay. Some polynomials you can factor by grouping. And then it means just that. We're going to group it together. We're going to pull out what the group has in common. Okay. So they have it here in letters. If we have RA plus RB plus SA plus SB, the first two have R in common. The back two have S in common. So we can pull those out. And that leaves us with an R and an S. So then, here's how it goes. Oops, wrong button. I want this one. So what they have in common, this one has an R in common as is color coordinated. And this one has S in common. So they pulled out the S and they pulled out the R. But then the two separated by the plus sign have something else in common themselves. So we can pull out another thing they have in common, which is that A plus B. And it leaves us with the R plus S all alone. We pull the A plus B off the R. We pull the A plus B off the S. Okay. So let's look for that here in the example that they give. You could try to look for greatest common factor, but they don't all have numbers and they don't all have letters. So we're going to take z to the third plus 5z squared minus 4z minus 20, and we're just going to group them together and pull out what they have in common. So I'm going to group this part, and I'm going to group that part. And what I pull out is going to have a sign with it. So what is common in z to the third plus 5z squared is just z squared. And that leaves me with z plus 5. Now what I really want to do is get z plus 5 left over in this parenthesis. So what I'm going to pull out, because they're both negative and 4 goes into both of them, is I'm going to pull out a negative 4. That leaves me with z plus 5. Now I've got this in common between both. So I've got z plus 5 times what's left over, z squared minus 4. Now you might think, oh, I'm done. I'm ready to go. But if we look right at this guy, that's a difference of squares. Z is squared, 4 is 2 squared. So we actually have to keep going because remember, we want to factor it all the way down. So we're going to use that pattern. Each one gets a z, each one gets a 2, one's plus, one's minus. That's the difference of squares pattern. Now we're finished. Okay. Over here was close, but it's not the most right answer. An expression in the form of AU squared plus BU plus C, where U is an algebraic expression, is said to be in quadratic form. Basically, they're taking something that is not a squared and they're turning it into something that is squared that looks squared. So the u is representing some amount. It's a variable, like all of the letters mostly in math are, except for I. Okay, so let's look at A. We've got 16x to the fourth minus 81. Right now I notice it's two pieces and it's got a minus in the middle. I know that 8 is 9 squared. I know that 16 is 4 squared, but x is to the fourth. Okay. But what I can do is I can consider x, right? Because what makes 4? Well, 2 times 2. So if I consider that x to the fourth is x to the 2 times 2, I can use the property of exponents that says if I'm multiplying the exponents, it was a power to a power. Because when you have a power to a power, you multiply them. So I could actually pull that and separate it out so that it's x squared squared. Now the whole front thing is a squared. I basically have 4x squared squared minus 9 squared. Difference of squares. So I have 4x squared in the front one. I have 4x squared in the back one. I've got a 9 in each. One's plus, one's minus. And at first glance, it looks like I'm finished. I did my factoring, right? But this one is also a difference of squares because 4 is 2 squared and 9 is 3 squared. Sum of squares doesn't do anything. So 4x squared plus 9, that one's done. But the difference of squares can separate. I can make this a 2x in each. I can make it a 3 in each. One's plus, one's minus. And we get to the end. Let's look at B. B for blue. We got 3p to the 8th plus 15p to the 5th plus 18p squared. Well, let's pull some stuff off of there. 3 goes into all of them. P squared goes into all of them. That leaves me with p to the 6th plus 5p to the 3rd plus 6. Now, if it was p squared plus 5p plus 6, factors of 6 that add to 5 would be 2 and 3, and it's factorable. The problem is that it's p to the 6th. I need it to be squared, and the problem is p to the 3rd. I need it to be squared. But if I treat this as one whole thing, this is where they get the u from that they're talking about, an au squared plus bu. Instead of doing x like we normally see, they do a u. Remember, u is an algebraic expression. An expression involves a number, a letter, or a combination of both. So I could treat this as my u. And if I treat that as my u, p to the 3rd, p to the 6th is like p to the, well, it's supposed to be p to the 3rd squared, because 2 times 3 is 6. That's like my u. So if I say p to the 3rd equals u, and then I do 3p squared u squared plus 5u plus 6, I can now factor that. 3p squared, each one gets a u. Factors of 6 that add to 5, 2 and 3, both positive. And now all I do is just replug what u was equal to. 3p squared, p cubed plus 2, p cubed plus 3. Those are not sums of cubes, so I am finished there. Now, I don't really do this step or that step. I go back up to here, and I just put the p to the 3rd in parentheses, and then I just turn this guy, say, okay, well, you're now squared to the 3rd and squared. And I just use p to the 3rd as the thing, and I know where that is. If you want to use the u's and substitute and then substitute back, that's great. If you want to just use the parentheses and write it as is and just treat it like it is in quadratic form, it's not really a quadratic. It just has the form. That's why it's like that. Either way is fine with me, but you need to recognize that the thing that's not really squared could be treated like it was squared. Okay? Here's some. Factor them all the way down. There's a mix of them in there. They may or not be in the order we just talked about them. So start at the 4, go to the 9. Pause it, try it, come back. Okay, here we go. Number 4. A to the 3rd plus 27. 27 is 3 cubed. So that's a pattern. It's a sum of cubes. That one's a plus, that one's a minus, that one's always plus. It's matchy-matchy. A goes here, 3 goes there. A squared, 3a, 9. Done. That's how you use the pattern. Okay? Let's look at number 5. 6z to the 5th minus 750z squared. Let's see. 750 divided by 6, 125. I like 125. Let's do 6z squared coming out of there. That leaves me with z to the 3rd minus 125. That's 5 cubed. So that's 6z. This one's going to be minus, plus. It's always plus at the back. This one gets a z. That one gets a 5 squared. No, it gets a 5. This one's z squared. That's 5z. 5 squared is 25. Let's look at 6. X to the 3rd plus 4x squared minus x minus 4. It's got 4 parts. I am probably going to have to group these together because they don't have any type of common factors whatsoever. So I'm going to group the first part and I'm going to group the last part. What I can take out of the first part is an x squared. That leaves me x plus 4. So what I want to take out of the back one is going to leave me with an x plus a 4. I have an x, I already have a 4, so I don't need to take any numbers and letters out. I just need to take out the negatives. So I'm going to take out a negative 1. That'll leave me a positive x now and a positive 4. I know this because if I distribute back in, it gives me negative x and negative 4. Now they still have x plus 4 in common, so I got x squared minus 1. And I'm going to pull out an x plus 4. Now, I should circle it, but x squared and a negative 1. Negative 1 is like negative 1 squared. That's a difference of squares. So I get to go a little further. Each one gets an x. Each one gets a 1. One's positive, one's negative. And we still got that x plus 4. That's what it all goes down to. Always check and make sure that you're factored all the way. Once you get down all the way, you're good to go. Now let's look at 7, 8, 9. The whole reason why 6 is afraid of 7. All right, 3y to the 3rd plus y squared plus 9y plus 3. I'm going to group these first ones, group these last ones. I'm going to pull out y squared, leaves me 3 plus, nope, it leaves me 3y plus 1. In here, I'm going to pull out a 3, which leaves me 3y plus 1. That's what I have in common. So we got y squared plus 3 times 3y plus 1. And y squared plus 3, it's definitely not a difference of squares. It's not a difference, and 3 is not a square. So we're stuck right there. Let's look at 8. Negative 16n to the 4th plus 625. It's a plus, it's 2 parts, so squared isn't going to cut it. Okay, that's not going to work really, unless I pull out a negative number. That negative 16 is a clue, so I'm going to pull out a negative number. Let's see, what goes into that? Probably, if I do, let's see, 625 divided by 16. Nope. Divided by 8. Nope. Divided by 4. Nope. Divided by 2. No. Was it 625? It's definitely 625. Well, Is 625 a perfect square? Let's see, 625. Oh, it's 25 squared. That's what we need. So we can't actually pull anything out because they're not both even. Nothing goes into both of them. But I can pull out the -1. And that gets me 16 into the fourth. Now, minus 625, which we just saw was 25 squared. We know this is 4 squared. And we know that n could be n squared squared. So, -1, and we're going to do a difference of squares. Each one gets a 4n squared. Each one gets a 25. One's plus, one's minus. These are both difference of squares again, because that's 2 squared and 5 squared. That's a sum, doesn't do anything, so we can go -1, 4n squared plus 25. That's supposed to be a 2. And we get 2n and 2n, 5 and 5, one's plus, one's minus. And we are done with number 8. -1, 4n squared plus 25 times 2n plus 5 times 2n minus 5. If you're following along on your book, which you should be, hopefully they got that same answer that we did. Oh, you can't see those because they're monitoring progress. Take that back. But that's what the answer should be. And let's check number 9. 5w to the 6th minus 25w to the 4th plus 30w squared. I can already tell it's probably going to be a quadratic form because it's 3 parts. It looks quadratic, but it's not. So let's pull out what we can. They all have a 5 factor. They all have a w squared factor. That leaves me w to the 4th minus 5w squared plus 6. I'm going to treat this as one whole thing. So I'm going to turn this into w squared squared. And now I'm looking for factors of 6 that add to 5. Factors of 6 that add to 5 are your 2 and your 3. Each one of these gets a w squared. They're both, because they're add to negative, both have to be negative. 2 and 3 aren't squares, so the difference of squares doesn't work, and it stays just like that. Next video, we'll pick up the rest of the lesson.